Hello again, guys. I hope you're having a great day. If you remember the very beginning of this unit, I told you our big goal was to be able to work those reaction stoichiometry problems with your limiting reagents and your percent yield if the reactants that you were given are liquids. In our previous unit, we worked those problems if you had solids. And in our next unit, we're going to talk about how you work those problems if instead of liquids or solids, you have gases. So at some point, we need to stop and talk about solids, liquids, and gases. Compare the three states of matter. Talk about how you convert from one state to the other. And I'm choosing to have that discussion now. So we are going to talk today about the difference between solids and liquids and gases. And we are going to do that using two graphs. These graphs are called phase change diagrams, meaning changing phases of your states of matter, changing from a solid phase to a liquid phase to a gaseous phase, so on and so forth, okay? So our notes today are going to really be filling out a couple of graphs. It's important that you truly understand each and every aspect of this graph. I recommend that you take notes in different colors. I think you're going to need maybe 4 to 5 different colors. And I also recommend that you study this section by redrawing the graphs and talking out or writing out what's happening at each and every point. So pause the video until you've got your colored pencils, markers, whatever you want to use out, and then restart when you have your resources gathered. Okay, our first graph, we are going to graph the amount of heat added. Okay, so I want you to imagine, if you will, say putting a pot of ice on a stove, and you turn on the stove and you gradually add more and more and more heat. You leave the pot on the stove for a longer period of time, or you can think about it as truly just cranking up the temperature, cranking up the heat on your stove. So x-axis is the heat added. Your y-axis is going to be your temperature. Okay, so we need to stop for a minute and talk about temperature. What is temperature? What does that word mean? So your technical definition of temperature is average kinetic energy. Average kinetic energy. Okay, let's talk about that in detail to make sure you understand it. Ladies and gentlemen, let's assume that we have a sample of a liquid, like just a cup of water. These would be the molecules in your liquid. Liquids are a little spaced out further than a solid, not as evenly organized. And these molecules will have energy. But part of that energy, a good bit of that energy, will be used to cause the molecules to move. Any energy associated with motion is kinetic energy. Kinetic energy is your energy of motion, or energy associated with movement. Now, these molecules will have different amounts of energy. Some of them will have less energy, and therefore they will be moving slower. Some of them will have a lot of energy on the high end, and they'll be moving much faster. Some of them will have, like a median amount of energy. If you take a thermometer and you insert that thermometer into the sample, these molecules up here are going to collide with the thermometer because they're moving. When they hit the thermometer, some of the energy of the molecules will be transferred to the thermometer itself. And every thermometer, or old-fashioned thermometers, the ones that we're using in lab, will have a very small, hollow middle column. And in that column, you'll have a liquid. It used to be mercury. Now it is an alcohol solution. As these molecules from your liquid collide with the thermometer and transfer energy, this liquid will expand as it gains energy. It will start moving faster as well, and it will use that energy to expand, and it moves up this column. Okay, so the greater the expansion, the more energy has been transferred to the thermometer, and therefore the more energy that was stored in this liquid solution. Now, some of the molecules are hitting the thermometer and transferring a small amount of energy. Some of the molecules are transferring a large amount of energy. So what your thermometer is doing is kind of taking the average of all of that. So when you are recording an object's temperature, you are not measuring only the molecules with the most energy, nor are you measuring only the molecules with the least amount of energy. What you're doing is you're taking all of those energies and getting an average. So we've talked about this in class before. It's important if you're taking the temperature of your body, that recording, that number that you're getting is not the energy of every single molecule. Some of the molecules in your body are going to have more energy and some are going to have less. So that number that you're getting is just the average motion of the molecules in the sample that you're testing. Okay, so one more time, this is super important, guys. Some of the molecules in the sample will be moving faster, some will be moving slower. If you take the average motion, the average energy due to movement of all of the molecules in the sample, that is called temperature. So on this first graph, we are, of course, graphing temperature on your y-axis, and your temperature, just a normal graph, temperature will increase as you go up the y-axis, versus heat added. Okay, the first part of this graph is going to look something like this. It's just going to be a line that goes up with a positive slope. This part of your line is going to represent a solid. So in your mind, I want you to think of putting ice cubes in a pot. Let's just make it simple and keep our sample water. You put a bunch of ice cubes in a pot, put a thermometer in the pot, put the pot on a stove, and turn on the stove. So we are adding heat, we're moving in this direction, okay? And we should see the temperature on the thermometer start to go up. That should just make sense to you. Now, the solid molecules, when you have a solid, the particles, the molecules are in an orderly structure. They are called a lattice structure, meaning the molecules have a nice, neat, orderly pattern to their organization, to the way they line up. As you add heat, the molecules are going to use the heat energy that you're adding to move, and they will start moving faster. Now, when it's a solid, the way they move is they start to vibrate. And they will start to vibrate faster and faster and faster. But notice I haven't said that the molecules change positions. If it's a solid, the molecules are always going to remain in this nice, neat, orderly lattice structure. Now, since we're changing the energy of motion, we are changing the kinetic energy. And therefore, temperature changes. So let's add to your notes, they vibrate faster, meaning the kinetic energy changes, therefore the temperature changes, but they remain in a fixed position. But remain in a fixed position, or they remain in the same location. Okay, meaning if you, sitting in your chair right now, are a solid molecule, and I give you energy, you start wiggling around in your chair, but you do not leave your chair. Same for the solid molecules. Think of them as kind of being super glued into that position. They can wiggle as much as they want to, but they cannot pick up their feet and move and walk around. They cannot change their location. So as we move up this graph from left to right, what I'm saying is that your molecules remain in the same spot, but they start to wiggle faster and faster and faster, vibrate faster. Therefore, they are moving faster. So you are changing kinetic energy. In this case, we are increasing kinetic energy, and therefore our temperature increases as well. So you should see, as you got that ice, that pot of ice on the stove, as it continues to heat, you will see the temperature increase. But then something very interesting happens with your temperature. You will see that your temperature levels out at the next part of our graph. So this next part of our graph represents a phase change. If we are moving from left to right, that means we are changing from a solid to a liquid on the graph, so that is melting. If you are reading the graph in the opposite direction, that means you're changing from a liquid to a solid, so of course that is freezing. Okay, why in the world does our temperature remain constant? I want to remind you that temperature is average kinetic energy. So if our temperature remains constant, that means the kinetic energy, the motion of the molecules remains constant. But you know that in order to get something to melt, you have to continue to add that heat energy. So what's happening? Well, in order for something to change from a solid, which has this nice lattice structure down here, to a liquid, not only do the molecules have to move faster, have to vibrate faster, but they also have to start spreading apart. You have to change their spacing. You have to take the molecules and you have to spread them apart from each other, meaning you have to change the distance or the spacing between molecules. Well, energy due to something's position or location or spacing is not kinetic energy, it's potential energy. So during this phase change, the energy that you're adding is not being used to make the molecules move faster. It's not being used to change the kinetic energy. Instead, it's being used to change the spacing. So down here, let's add to your notes, the spacing between molecules changes. Meaning in one direction, the molecules are spreading apart from each other. That's if you're moving from solid to liquid. If you're freezing, of course, instead of spreading apart, they are moving closer together. And therefore, on this part of the graph, and this is the really important part, I'm going to write this up here at the top. Your kinetic energy remains constant, but the potential energy changes. So kinetic energy is constant, and therefore the temperature is constant. But the potential energy changes. And since that thermometer doesn't measure potential energy, since the thermometer only measures the kinetic energy, you won't see a change on your thermometer. If you have a measuring instrument that measures potential energy, you would see a change at this part on your graph. Okay, so one more time. As I move from left to right along this part of the graph here, as I move from left to right in this direction, the molecules will use the energy that you are adding to spread apart, to change the spacing between molecules. So the molecules are vibrating faster and faster and faster, and then they reach a point where they can't vibrate any faster and remain a solid, and so the energy that you're adding is used to space the molecules apart from each other. At that point, we undergo a phase change, and the potential energy changes. So the molecules don't vibrate any faster, and therefore the kinetic energy is constant, and therefore your temperature remains constant. In one direction you have freezing, and the other direction you have melting. Okay, now it's important that we extrapolate back from this line to your y-axis. And where that flat line, where your phase change intersects your y-axis, that by definition is your freezing point. Your freezing point is the temperature at which this phase change occurs. The freezing point is the temperature at which something freezes. Notice it is also the temperature at which something melts. So water freezes at 0 degrees Celsius, but it also melts at 0 degrees Celsius. We call it just the freezing point. You could call it the melting point as well if you want, but just typically we don't. We use one term for it, freezing point, and I'm expecting you to know that the temperature at which something freezes is the same at which it melts, and therefore freezing point is also the temperature at which something melts. Okay, the next part of my graph I'm going to do in brown. I'm going to clean up some of this right through here just so I have a little bit more room. So the next part is going to represent the substance in a liquid phase. So as a liquid, my graph is once again going to increase, have a positive slope, so just a straight line. So this part of the graph represents the substance in the liquid state. Now, instead of being in that nice, neat lattice structure, your molecules are spaced further apart. Along this part of the graph, the heat that you're adding is being used to make the molecules move faster, physically vibrate faster, and move past each other at a faster rate. Okay? And so because the energy that's being absorbed is affecting the motion, then this part of the graph changes your kinetic energy. So your kinetic energy changes because the motion changes, and therefore your temperature changes along this part of your graph. If you are moving from left to right on this part of the graph, then your kinetic energy, of course, increases. Molecules move faster, they're moving past each other faster, and therefore your temperature will increase as you move from left to right. Okay, when we get to the next part of your graph, you're going to see that it flattens off again. Right through here. Let me do that in a different color. I'm going to do, that looks a lot similar, very similar to the blue that I started with. So I'm going to do that in orange. So along this part here, your temperature will flatten out again. We will have another phase change. If you are moving from left to right on the graph, that means you will be moving from a liquid to a gas, and that is boiling. If you are moving from right to left, that means you are condensing, undergoing condensation. Because we are undergoing a phase change, once again, the energy that you are adding is being used to change the spacing between the molecules. To change from a liquid to a gas, the molecules have to move faster, but they also have to spread apart from each other. So along this part, the heat energy that you're adding is being used to spread the molecules out from each other. And therefore, along this part of the graph, the potential energy changes. The spacing between molecules changes. If you're moving from left to right, the spacing between molecules increases. But because the energy that's being added is not being used to make the molecules vibrate or move faster, instead change the potential energy, the kinetic energy remains constant. And therefore, along this part of the graph, the temperature is constant as well. Okay? If we take this and we extrapolate back, so I'm extrapolating from this flat line back over here to my y-axis, where that flat line intercepts your y-axis, that is called the boiling point. So whatever this temperature is right here, that will be the temperature at which this substance boils. It's also the temperature at which something condenses. Okay, so the boiling point is the temperature at which the substance boils. It's also the same as the temperature at which it condenses. Now, boiling point can also be referred to as heat of vaporization. I see that phrase a lot. If you see heat of vaporization, what you're thinking about is the boiling point for me. We'll talk about heat of vaporization in much greater depth in second semester. But for right now, if you see that phrase, I want you to think boiling. Okay, the last bit of your graph, and I'm going to erase a little bit of this so I have a little room to work. Okay, along our last part of our graph, we're going to once again see that straight line with a positive slope. Along this part of the graph, the substance will exist as a gas. The molecules are now spaced very far apart from each other. And any heat energy that you continue to add to those gas molecules is going to change their motion. It's going to make the molecules move faster, vibrate faster, and therefore your kinetic energy will change, but your potential energy will remain constant. Your kinetic energy changes. Okay, so if you move from left to right along this section of your graph, your temperature increases because the molecules are using the heat energy that you're adding to move faster, to move past each other at a faster rate, but also to vibrate faster as well. And since the heat energy that's being added is used to change the molecule's motion, the kinetic energy changes, and since temperature measures kinetic energy, your temperature increases as well. Okay, so guys, one more time, I'm going to go through and just kind of recreate this graph and talk about what happens at each point, and you should be able to do the same. If I start with a solid substance, the molecules are close together. They're in a nice, neat, orderly structure. As I add heat energy, the molecules will use that energy to vibrate at a faster rate, but the molecules will not change their position. They remained in the same spot. Since the molecules are using the heat energy that's added to change their motion, the kinetic energy changes. If I'm moving from left to right on this graph, that means the kinetic energy is increasing. And since temperature is a measure of kinetic energy, temperature is your average kinetic energy, your temperature will also increase. As I get to a point where the molecules cannot vibrate any faster, the heat energy that I'm adding instead will be used to space the molecules apart from each other, to spread them apart from each other. When that happens, I will have a phase change. The temperature remains constant during a phase change because the molecules are using the heat energy that you're adding to spread apart from each other, to change their location, to change their potential energy, instead of changing the kinetic energy, the energy of motion. Once the molecules are spaced far apart from each other, the substance will exist in a liquid phase only, and the heat energy that you are adding will be used to increase the speed, the motion of the molecules, and therefore the temperature changes again. Okay? Then I reach a point where the liquid molecules are moving as fast as they possibly can. Heat energy that you add is now used to spread the molecules apart from each other, and I undergo another phase change. Your temperature remains constant during the phase change because the energy that you're adding is used to change the position, the spacing between the molecules, instead of changing the energy, instead of changing how fast the molecules move. And then I get to a point where the molecules use the energy to change their speed once again. So from here to here on your graph, the substance exists in the solid state. The molecules use any heat energy that you add to change the motion, so therefore the kinetic energy changes along this part of the graph. When you get to the next section of the graph, the flat part of the graph, okay, over here on the left-hand side, you have more solid, and then the molecules start spreading apart. The molecules absorb the heat energy that's being added and use it to change their spacing. So if we're going from here to here, we're changing from a solid to a liquid. So right here, you've got a lot of the molecules close together in that nice, neat, orderly lattice structure. Over here, the molecules are more spaced out. So you have, along the graph, you have lots of solid spacing out turning to a liquid, more of it turning to a liquid, more of it turning to a liquid. It's all a liquid. And it's important for you to remember along this part of the graph, your temperature remains constant because the spacing changes, not the motion, but the spacing, and therefore the potential energy changes. If you extrapolate from that flat line back, whatever this temperature is right here where that flat line intersects the y-axis, that is called your freezing point, which is the temperature at which something freezes. It's also the temperature at which something melts. If you're moving in this direction, you're changing from a solid to a liquid, you're melting. If you're moving in this direction, you are freezing. So along this section of your graph right here, you're going to have a mixture of solid and liquids. The closer you are to this side, to the solid side, you're going to have more solid. The closer you get over here, you're going to have more liquid. So you've got both solids and liquids present at the same time at that section, and the amount depends on which part of that flat line you're on. Are you at the point where the molecules are closer together, in which case you're going to have more solid, or are they more spread apart, in which case you're going to have more liquid? Okay, when you get to the next part of the graph, one more time, this represents the liquid phase, and your motion of your molecules is changing, therefore your kinetic energy changes, therefore your temperature will change again, meaning the molecules are using the energy that you are adding to move faster. And the further up you go on this line, moving from left to right, the faster the molecules are moving. So down here in this part, the molecules are moving a little slower. Up here, they're moving much faster. So the motion will change and vary all along that line, molecules moving faster and faster and faster. When you get to this part of the graph, you have another phase change. Your spacing changes, and therefore your potential energy changes. Right here, you're going to have more liquid, and then the molecules are going to spread further apart from each other. Right here, you'll have more or all gas once you get to the end of this flat line. So how much liquid or gas you have depends on where you are on this line and how far apart the molecules are from each other. The further apart they are, the more gas you're going to have present. Okay, and then finally along this part of the line you have only gas present, and your kinetic energy is the only thing changing, therefore the motion of the molecules is changing, therefore your temperature is changing as well. Okay, this graph kind of explains why steam burns are so bad. If you look, you've got the maximum amount of energy, kinetic energy, up here at the top part of your graph, which case the molecules exist in the gaseous state. So that's why, you have to be really careful. Any of you who like to cook, you hear if you've got a pot of boiling water, you always open the lid so that the lid is between your face and the pot, meaning you lift the lid towards your face, not away from you. And the reason for that is the lid kind of blocks the steam from coming into contact with your face. Steam burns are super dangerous because those molecules contain so much energy, and that energy will be transferred to your skin, to your body, and cause severe damage. And it's because they have more energy contained in those molecules than, of course, your solid or your liquid molecules. I have a friend who had a severe eye burn because she popped a bag of microwavable popcorn, and when she got it out of the microwave, she opened it and looked right down into the bag, to smell the wonderful buttery popcorn smell. But the steam that was released hit her right in the eye and caused severe damage. Okay, and then, of course, let me clean up this just a tad. If I extrapolate back from this flat part of your graph here, this phase change, if I go back over here, wherever that intersects with the y-axis, whatever this temperature is, that is called your boiling point. That is the temperature at which boiling occurs if you're moving in this direction of your graph. It's also the temperature at which condensation occurs if you're moving in this direction, and that is also called heat of vaporization. So guys, what this part right here means is if you put a pot of water on the stove and you put a thermometer in the water and you start boiling it, while you see the boiling occurring, the temperature of the liquid will not change. The thermometer reading will not change during that process. Okay, so a phase change is occurring in lab because your temperature remains constant. You know exactly when that boiling starts, even if you don't see any bubbles in the water, because your temperature flattens out, your temperature stops changing. Okay, guys, I want you, just on the side of your notes, to give me a tiny little sketch of a graph. I want you to show me what your graph would look like if instead of graphing kinetic energy versus heat added, we graphed potential energy versus heat added. And then I want you to do another graph, which would show your total energy versus heat added. Okay, pause the video, think through what would those graphs look like in comparison to the one we just did. And when you're ready, restart the video. Okay, for potential energy, when the substance is in the solid state, your potential energy does not change. The position of the molecules does not change. They stay in that same location, so potential energy would be constant. During your phase change, your potential energy would increase. During the substance, when the substance exists as only a liquid, your potential energy stays constant again. The molecules use the energy to move faster, not move further apart from each other. Then you have another phase change, and then you have your gas. So this would be your solid, this would be your phase change, this would be your liquid, this would be your phase change, and this would be your gas. Your total energy versus heat added, well, your energy, if you add up your potential and your kinetic energy, it's always increasing. So your total energy versus heat added graph would look like this. Okay, the second graph I want to talk about today is a graph of pressure versus temperature. You're going to have pressure on your y-axis. And by pressure, I mean atmospheric pressure. I mean pressure from the molecules in the environment pushing on the substance that we're talking about, on the molecules, the chemical that we're talking about, okay? Not vapor pressure. And then on the x-axis, we're going to graph temperature. Now, this graph is very interesting because what this graph shows us is that you can change something's state of matter by changing the atmospheric pressure. Meaning I can cause water to boil without adding any heat. Okay, let that sink in for a minute because you've probably never seen that in your life. Let me say that one more time. You can change water's state of matter without changing the temperature. I can make water boil without putting it on the stove. I can make water boil by just changing atmospheric pressure. What in the world? Okay, let's get some details down on your graph and then we'll come back and revisit that statement. Any combination of pressure and temperature that puts you on this part of your graph over here, this area of your graph, those of you in calculus should feel comfortable calculating that area between those lines. Anything that exists in that part of your graph will be a solid, okay? Anything that exists over here in this part of your graph, anywhere in here, will be a liquid. And some students think of this as the butt diagram, because if you do, then you will never forget that this section of the graph down here, any combination of temperature or pressure that puts you in that section of the graph, the substance will exist as a gas. Okay, anytime you change from a solid to a liquid, now we could do that by keeping the pressure constant and increasing our temperature, or we could do that by keeping the temperature constant and increasing the pressure. So anytime you cross from solid to liquid, this represents melting. Anytime you do the opposite, you go from a liquid to a solid at any part of the graph, so liquid to a solid, you can do that by keeping the temperature constant and decreasing the pressure, or you can do that by keeping the pressure constant and decreasing the temperature. Of course, that would be freezing. Okay? So, guys, what that means then is this part right here, this solid line, okay, let me darken that so you can see exactly what I'm talking about. This line right here Okay, so this solid line that separates your solid from your liquid state, if you extrapolate from that line down to your x-axis, wherever that intersects your x-axis, in this case, that would be your freezing point, okay? Which is also your melting point as well. All right, let's talk about changing from a liquid to a gas. So we can change from a liquid to a gas by keeping the pressure constant and increasing the temperature, or by keeping the temperature constant and decreasing the pressure. Anytime you do that, change in either direction, that represents boiling. We can go the opposite direction. Anytime you change from a gas to a liquid, now we can do that by keeping the pressure constant and decreasing temperature, or keeping temperature constant and increasing pressure. That, of course, changing from a gas to a liquid would be condensation. Okay? Now, this graph enables us to talk about one other phase change that our last graph did not. What happens if you change from a solid directly to a gas? You can do that by keeping your pressure constant and increasing your temperature by heating the substance, or you can keep the temperature constant and you can decrease the pressure. So this is a really cool phase change. This is called sublimation. Sublimation means you can change directly from a solid to a gas without going through the liquid phase. Dry ice is a perfect example of this. You can also go in the opposite direction. You can change from a gas to a solid. That is called deposition, but I very rarely hear anybody talk about that or ask you about it on the AP exam. So I think if you know sublimation, you're good. Okay, let me show you an example of dry ice and sublimation in case you've never seen it.
Right, I see it.
And dry ice is solid carbon dioxide. It's 109 degrees below zero, hence the gloves. You don't want to touch it with your bare hand. You could get frostbite.
Wow.
Okay? And so the neat thing about dry ice and where it gets its name from is that it never changes to a liquid at atmospheric pressure. It changes directly from a solid to a gas. And so you can see that.
Hypotransvaporation.
Really?
I don't know.
I've never heard of that. Right. We call it sublimation. Okay. In fact, go ahead and toss some of this into our cylinder here. You can't see the carbon dioxide gas because it's invisible, but if you drop some in the water, you can get an idea of how much gas is actually coming off.
Yeah.
Okay, and that's sort of the spooky thing you can do during Halloween is to create those bubbles. Now, I said you can't get liquid carbon dioxide at atmospheric pressure, but what you can do is if you pressurize carbon dioxide gas, like in this CO2 extinguisher, you can get it into a liquid form, and that's how they make dry ice. They'll take liquid carbon dioxide, and we're just gonna squirt this on the table here. And you get a buildup, that fine powder, and your pants as well. That fine powder is actually, here, go ahead and pick that up.
Okay.
Show that.
Whoa.
Yeah. So you got a little bit of dry ice. Now this is terribly inefficient.
Don't try this at home.
Don't try it at home. Manufacturers would actually take that light and soft, fluffy powder and compress it into these blocks, okay, to make it much, much harder. And that's where you get dry ice from. Now, the other cool thing that's happening with dry ice from a chemistry perspective is that when you put carbon dioxide into water, it actually creates some carbonic acid in the water. So, Tony, go ahead and drop in some more into this one.
All these?
Yeah. In this container, I've got an acid-base indicator. So the liquid will change color as it turns from an alkaline solution into a more acidic solution. So you get that cool sort of Halloween orange sort of color.
Yeah, the pH.
But the pH is changing, exactly.
Okay, guys, so sublimation's pretty cool because you saw the dry ice, the solid carbon dioxide changing directly to a gas without leaving any liquid behind. You can get it, you can force it to become a liquid by changing the pressure or the temperature or both, but it doesn't have to. Okay, one other thing that I want to add to this graph, let's kind of darken this line right here between your liquid and your gas. Any temperature that you extrapolate from that line, so let's say I extrapolate from this point down wherever that intersects your x-axis, of course, that would be your boiling point. the temperature at which the substance would boil. So this dark line here represents your boiling point, if you extrapolate to the x-axis, and this dark line over here represents your freezing point. Okay, a couple of other vocabulary words that you need to know for this graph. And I'm going to kind of clean up my graph just a little so you can see this a bit better. Okay, the first one is going to be this point right here on the graph, which is the intersection of your solid, liquid, and gas. That is called the triple point. And it's called the triple point because that is the temperature and pressure at which all three states of matter exist simultaneously. You will see the substance in the solid, the liquid, and the gaseous state of matter all at one time. And that is really hard to do. The conditions, the pressure and temperature at which that happens will vary from chemical to chemical, but it's really cool if you can ever see that. We can do that with dry ice. I'm hoping once COVID kind of calms down, we'll be able to do a little activity with dry ice, and you can actually see the triple point of carbon dioxide. But for right now, that pressure and temperature is called the triple point. So the conditions at which all three states of matter exist at the exact same time. And then this point up here on your graph is called the critical point. And the critical point is the pressure and temperature beyond which the substance can only exist as a gas. There is a point at which you can't control whether the substance is going to be a solid or a liquid. There is a point at which the temperature gets so high that the substance can only exist as a gas. So your critical point definition is the temperature beyond which the substance only exists in the gaseous form. Okay, so if you will, kind of beyond that point on your graph, it can only be a gas, is kind of what I'm saying. There is one exception to that. That's something called a supercritical liquid, and we can talk about that in more detail in second semester if you're interested. Okay, next I want to show you a couple of little examples, some cool videos. I started this graph by saying we can boil water without changing the temperature. So I want to show you that, how we do that and how that applies to this graph. To understand this video, you've got to know a little bit about the equipment. So this part right here is something called a bell jar. And a bell jar is just a really heavy, thick piece of glass that sits down on a thick rubber mat. So what you end up with is a sealed, closed container underneath the glass. You'll also notice there's like a little tube hooked to it. That tube is hooked over here to this machine, and this machine is called a vacuum pump. What a vacuum pump does, guys, is it removes atmospheric pressure. So you have gas molecules in here in this bell jar from the air, and this vacuum pump physically pulls them out through that tube, through that rubber tubing. So the vacuum pump is decreasing atmospheric pressure. It is physically sucking the air out of the container. And by doing that, you have fewer gas molecules present underneath the bell jar, so atmospheric pressure decreases. Now, to really understand this, you got to know one other thing. In order for something to boil, your vapor pressure must equal your atmospheric pressure. So let me say that one more time, and we'll get this in your notes later, but boiling occurs when vapor pressure equals atmospheric pressure. When those two forces are equal, when your upward and downward forces are equal, the substance will start to boil. Okay, so with that little bit of background knowledge, let's start the video.
All right, so let's get this going here. I've got a beaker of water and my vacuum chamber, plus I've got a vacuum pump here, and we're gonna get this set up, and we're gonna pull a vacuum on that water, and we should be able to make it boil without any heat. It's be a really cool thing. Let me show you.
So I want to point out, no heat was added. The guy, he did not put the water on a hot plate. He did not change the temperature of the water at all. He used cold tap water. You could put your finger in the water at the beginning. You could put your hand right back in the water at the end as the bubbles were occurring, and it is not warm. The water is not hot. The temperature of the water has not increased at all during this process. So what in the world is going on? How can something boil without changing the temperature? Well, to answer that, we're going to go back to this graph. I want you to remember that we started with liquid water, so we're starting with the substance in this section of the graph. So I'm just going to pick a point on that graph. It started, at like room temperature water was tap water, so I'm going to start about halfway. So let's say that dot right there represents the original temperature and pressure of the water in the beaker before we put it under the bell jar. Now, we did not change the temperature. So whatever temperature I'm at right now on the x-axis, I cannot change it. If I shift my dot over to the left or the right, that means my temperature changes. And that did not occur. The gentleman, he did not heat the water. So what we did do, however, is we removed atmospheric pressure. We changed the atmospheric pressure being exerted. We changed the downward force being exerted on the surface of the liquid. We had a certain amount of downward force. We removed the molecules in the atmosphere using the vacuum pump, and so now we have fewer molecules bouncing on the surface of the liquid, and therefore it is easier, it requires less energy for the molecules in the water to turn to a gas and leave the solution. So you can get something to boil at a lower temperature than normal. So what we did is at the same temperature, we lowered atmospheric pressure. So we crossed from a liquid to a gaseous state by changing only the pressure, by keeping the temperature constant. And you see, by doing so, changing from a liquid to a gas, we're causing boiling to occur, keeping temperature constant and decreasing our pressure. Okay, let me show you another example of this. And this one's really cool. This is one that you can do on your own at home.
For this project, grab a bottle of room temperature soda and start shaking it violently. We want as much pressure to build up inside as we can get. Now I've done this with these 500 milliliter bottles and set them in the freezer for 3 hours and 15 minutes. This is the point when they're colder than freezing, but not actually frozen. Now you can show your friends that it's just a normal soda, but watch what happens if we simply release the pressure, tighten the cap, and turn it upside down. In just 3 seconds, the entire bottle is turned to an icy soda slush. Pour it in a glass and you'll get a good idea of how thick the slush really is. And when it starts pushing up at the top, you can see it's a light and fluffy, delicious carbonated ice. Now let's try removing the pressure very slowly. This is going to take a bit of patience, but when you get the cap off, you might notice your soda didn't freeze. If you pour it into a frosty bowl that just came out of the freezer, it'll ice up right before your eyes.
So you can make your own slushy or icy at home using this. Okay, let's explain it. Once again, we're going to go back and use this graph. Okay, for our last explanation, when we were talking about boiling water at room temperature, boiling water without heating it, I started right about here. I'm going to move my dot up and to the left. I'm moving it to the left because we put the soda in the freezer, so my temperature is lower. I'm starting not with room temperature, water like the example, but cold soda since it stayed in the freezer for a while. I'm also raising that dot. And the reason is we shook up the bottle. By shaking up the bottle, you're causing pressure to build up on top of the surface of the soda, so I'm increasing atmospheric pressure. So for this example, I'm going to start with a dot right about here, and you could even move it up and over a little further if you wanted to. Okay, so then, ladies and gentlemen, we put it in the freezer, we shook it up, and then we opened the cap. When we open the cap, we are releasing that atmospheric pressure. As that pressure leaves the bottle, atmospheric pressure exerted on the top of the soda will decrease, and so you will see a phase change from a liquid to a solid state. So you create your own little homemade icy. How cool is that? Okay, so anytime you cross these black solid lines on this graph, you will have a phase change occur. And once again, this graph is really cool because it shows that you can cause a phase change with a constant temperature. You can cause something to change states of matter without heating or cooling it. All right, excellent, ladies and gentlemen. If you have any questions or anything that I said was confusing, make sure you reach out to me.